Hello again. This is going to be a, hopefully not a real long video, but a video on kind of just discussing a little bit of theory of operation of IF transformers and just a little discussion about them in general and stuff. I may do a small little graph, just again, anytime I'm drawing stuff. I'm no artist, so without graph paper I tend not to get it really a well drawing done, but we'll do the best we can. Alright, I've got just a Gamble Sagamo radio here, model 750 schematic. It's an old radio, basically from the tubes. We've got 258s, 55 detector triode tube, dual diode triode, 245s push-pull output, and a 287 for our mixer oscillator. Now, in general, basically your signal comes in an antenna and you tune it, and in this case on this radio it's going to be amplified by an RF amp going through a tune circuit. We get to the mixer. Now, we've discussed this before. You have a local oscillator for a super heterodyne radio. It mixes with the incoming signal. The difference between the two ends up being your IF frequencies. In this case it's 175 kilocycle. Back in the day, in the 30s, a lot of experimentation, a lot of things were going on, so there's several different IF frequencies you can run across. The more common ones is 175, 165, 185, and then they jump up to 460, 465, 475, 485, and then there was a few 455s late in the 30s, and finally settled on that for a long period of time at 455, except for car radios, which generally run one half of the 455 at 262.5. And the reason why they do that is more for interference and noise suppression and stuff that may be picked up, and even though they try to filter as much from into the antenna, it seems that 455 some of that can get through, whereas at the half frequency point it doesn't. And of course this is coming from ignition system, alternator, things of this nature. Anyway, that now, what are these? We call them IFs, intermittent frequency. A lot of times they're called coils, which they are, but they're actually a true transformer. They're a tune transformer, meaning that the primary and the secondary, in most general sense, will be a tune circuit, and it will have a capacitor generally in parallel. They're generally tank circuits, although there are some where you only have one tuning on one. You can actually make an IF where you just have just one section and have a pickup off of it. You can either go direct pickup or you can go with another coil and pick it up. In any case, most standard ones has got a primary and secondary. They're both tuned. They will be tuned to the IF frequency just to allow it through. Now, when you look at an IF transformer, you'll see they don't look like most transformers you're used to, or even as far as that goes, other style transformers such as what you may find in your front end, such as your antenna, tuning coils, and maybe some other coils, or even your oscillator coil. A lot of these will wrap The tune circuit, or one of the primaries, will be a large wrapping of coil wire, and directly over top of it will be another coil, the secondary, wrapped over it. Real tight, close together, real close contact. Where on an IF, you have your two coils. They're really drastically separated. This is called loose coupling. The closer you move coils together, the tighter the coupling is. And what they're talking about, magnetic coupling. So the wider apart, the farther apart you move the coils from each other, the looser the coupling is. Now there's a reason for this. And the primary reason, or the biggest reason, is the looser the coupling is, the narrower the bandwidth is that can pass through, the band pass that these pass through. So it narrows it down, the looser the coupling. The tighter the coupling, the wider the bandwidth. Now, your front end coils, such as antenna and other tune coils, if you have an RF input amp, RF amp prior to the mixer, all those we want to be a wide band. It makes a lot easier to tune in radio stations. If you made those too narrow band, two things can happen. One, excuse me. One, you got to be careful about how narrow any band pass is, because a radio, an AM signal has a center carrier, but the audio is actually on what they call side bands. And at some point I'm going to discuss this. This video is not really set up to be doing that. It's a whole video by itself. So you don't want to be too tight, or you'll start losing your side bands, which would mean you'll lose your audio, a lot of your audio. The other problem is if your input section, your front end of your radio, is too tightly, too narrow bandwidth, too loosely coupled, what happens is it makes it a lot more difficult to try to adjust in when you're tuning the dial to get a radio station. They get to be really nitpicky about where they're located on the dial. In other words, you'll just go a little bit, just a barely little bit of turn, and you're either tuned in or you're not tuned in to that station. Well, that's not going to work with the general public. So you want to make sure that it's wide enough that it makes it easy to tune in, and as well as you can make sure you're keeping your side bands. The IF is different. It's operating at one frequency. It can be tighter. In fact, you want it to be tighter by tightening up narrowing that bandwidth, loosening up the coupling. That is called selectivity. That makes it more selective about the signal that can go through it, so that only what you're tuned into is what you're going to hear. So that's why they do this, and I'll kind of do a little drawing on it, but that's why these are spread out like they are on the form. Now, I had a comment on one of the videos about, I got an IF transformer sitting here, and I got wires coming out of it. And how do I determine which is the grid, which is the plate connection, which is the ground connection? Well, to answer that, first and foremost, if it's one that you're pulling out or half pulled out or whatever, before you ever pull out anything out of the radio that's got wires, connections, you should document that. Document with pictures, document with sticky tabs or whatever, or make you a little chart or something and saying that, well, you know, this colored wire went here, this wire went there, or however, so that you can document where all those connections are. Now, some IF transformers, like this one, at least one lead is real easy. Any lead that comes out the top and has this cap on it, that's the grid. So that automatically is a given. Not all IFs are like this. Newer ones, or relatively newer ones, you get in the 40s, they pretty much got rid of grid caps, put all the grids down below, connect to the tube socket. So you wouldn't have that. But the older ones, that is your grid connection. Now, in a general sense, grid will be green. Now, it may be like this one, and I don't know if you can see it very well on the camera, but it's a white wire with a green stripe going around it. So most likely it's going to be like that, but it can also very well be just a solid green wire. Some of the other wires in the radio, generally ground, which is hooked on the secondary, which is the same side the grid's hooked on. This side here, this wire leading down, which generally goes in the AVC circuit, is considered ground. It's usually black. Now, I'm saying all this in general because I'm going to come back and we're going to discuss a little more about these colors. As far as this side, the primary side of these, one side goes to B+, and the other side will go to the plates. Okay, the side going B+ is generally red wire. The side going to plates, if you actually follow the standard, is supposed to be blue, but in the case of this one, it's white, and that can be a normal thing. But you'll either see blue or white. In most cases, going to the plate. As far as the B+, generally most will run red. There are some out there will have maybe either brown, or I have seen them be white on some radios, but 99% of them, or at least 95%, will be red. Grid is another one, just like the plate, that can change colors. Sometimes it may be blue. Sometimes it may be yellow. And again, if it's cloth wire, generally they run a stripe. They'll have a base color and then run a stripe, whereas on rubber coated they just run solid color. Ground can be black or white, but for the most part it matters not anyway. If you get an IF transformer, maybe you need one, you go on eBay and you order one and you need it, alright, and you get it, and even though it may be something that they said, maybe the seller said came out of radio, the exact radio is yours, it could be a different run, could be any number of things, and it could very well, came out of the make and model radio. But I have seen, especially on some radios, where they changed IF transformers and ended up with different colors. Even though it's the same model, it was just a later serial number. So in any case, you got this IF transformer. Now you're going to have to try to determine what's going on with it. How does it hook up? If you do have a black, and you do have some of these colors I talked about, well, then it's not going to be quite so hard. If you don't, these are very forgiving transformers. You generally see that in tuned transformers that are loosely coupled. If they're tightly coupled transformers or coils are not as forgiving about this. But they're, when you got loose coupling and tuned circuit, tuned coils in the transformer, you can generally, without too much problem, have them out of phase with each other. In other words, what the signal going in, the winding is winding one direction, and how you got wired up, the outputs going a different direction. Matters not a whole lot. There may be a slight change in signal, but it's not going to be enough for you to even notice, as far as strength. The other thing too is I have two IFs here. I can tell you right now, this one's different than this one in which coil is primary and which coil is secondary. Here's your primary, because it's the B plus line. This goes to the plate. Primary is at the top of the coil. The coil normally sets, or top of the transformer normally sets like this, closest to ceramic. This is primary. This one down here is secondary. It's the one that goes to the grid. This one's just the opposite. Now, to really show you, I'd have to unsolder the cap, but trust me, it is. It's just exactly the opposite. The secondary is up close to the top, and primary is down here. Matters not. The only reason why they did this was because this one actually has a third winding in it, and you'll see this in some radios, especially radios with push buttons with some sort of automatic tuning. By the late 30s into the early 40s, they figured out that they were having troubles with tuning if you use the push buttons. You would end up with the selectivity being strong enough, because the IF transformers being selective enough, that trying to get them buttons adjusted exactly on where they needed to be, so that you hit it, your radio station comes in loud and clear, was a very difficult thing. So what they did was and this is the first IF, on the first IF transformer, the input transformer, they put another winding that would be connected in when you're using the push buttons, the automatic tuning. And what this did was, it was wound in such a way that it actually allowed to broaden the band with a little bit, widen it out, because it's setting this actually hooked into the same points as the primary does, basically kind of similar. It depends on the radio. Sometimes they hooked a little differently, but it acted as another primary input signal that is tightly coupled to the secondary, and widened it out a little bit, widened that bandwidth a little bit, just enough that them buttons could be just slightly off. They don't have to be dead perfect in their adjustment, and you still get a good strong radio station when you hit your button for that station. That's why they put the secondary down here, because putting up here, you would run these wires, even though they go inside, you're going to have to wrap a coil up here. And between these two, it could cause interference or problems. So it's better to keep it down here. So they had to move the secondary down here. So the point of all this is, it doesn't matter which one's primary and which one's secondary. As a general rule, IF transformers are one-to-one. They're not really designed to step up anything or step down anything. The amplification is done by the IF tube, and it's got plenty of gain, so they don't need the transformers doing anything other than being there to tune the circuit, so that I'm only passing my IF frequency. So they're generally one-to-one, which means that if you have a totally unknown transformer, other than maybe that it should be, your IF frequency, 455, or in this case 175 or 460 or whatever, but you don't know, maybe the wires are so, like this one here, they're so dark and it's very difficult to even make out what they are, colors. Then if you end up saying this one was the secondary and this one's the primary, it'll work. It'll work just fine. It matters not. And as far as testing these, like I showed on the one video, the last upload that was uploaded, where I was testing and using the scope, as far as testing them, matters not which one's going to be primary, which one's secondary, which ends you're going to connect to the negative of the generator or anything else. It matters not. The test will work just fine any direction you hook things up. And so will the IF in most of these. Now there are some IFs, especially second or output IFs, that may have a different turn ratio here, so they do, generally they step down as opposed to stepping up, primarily because there's enough amplification going on, enough gain and everything else, that, and the particular diode tubes that they're using may not like it may not like that strong of a signal going in, so they actually will try to reduce the voltage somewhat that it's seeing. But and you'll notice this because most of those schematics that you'll find will actually have a resistance on here, so you might see, say, like 20-25 ohms on the primary and like 5 or 10 or even 1 ohm or 2 ohms on the secondary, in some cases. As far as resistance goes, the relatively standard, at least after post-war, is generally in the 20 ohm range, but it can be somewhat different than that. But both primary and secondary, generally around 20, 22, somewhere in there, 23. I'm not going to really etch anything in stone because they're all different somewhat. Prior to the war, they could be anywhere from in the low 5s all the way up into the 40s. So anywhere in there, with the average generally around 7 to 10 or 12 ohms. Now, again, they can be any number of different sizes, so any number of different resistances on DC resistance. Don't sit here and go, wow, I got this old radio and he said, somewhere between 7 and 10, and I only got, I got like 40. There's got to be something going wrong here. Or he said post-war it should be 22 or 20 or 22, and I've got one here that says 7. That doesn't really mean anything. They do vary drastically from manufacturers. When I say generally, I'm saying that on average they're in that area. That doesn't mean all of them are by any means. So how do they work? Well, basically they're a transformer. We send a signal in. As the signal is changing, it's an AC signal, so it's expanding out at one point and then collapsing down, just like any other transformer. That is magnetically coupled to the secondary, so as that field expands from the primary here, it starts cutting the, as it expands, it starts cutting the secondary windings, which induces a voltage into those, which then feed to the grid of the next tube. Nothing magical. The only difference between these and, say, a power transformer or audio transformer is the fact that they have a tuning. They have, either capacitors that are tunable, padders, trimmers, or these are fixed and they've got cores in them. Ferric metal, iron core of some sort, powdered, that's hooked on. It either is just in there and it's got a little slot in it, or a hex in it that you can use your tool to turn, or it may be hooked onto a rod that comes up, brass rod that comes out, and you just turn it. That's the only difference. Otherwise they act just like any other transformer. Now, we will get into some other details about them. If you look at these two especially, when you look at them, they don't look like a normal amplifying tube per se. Most amplifying tubes, you see some sort of resistor or something on the plate, a plate load resistor, and stuff, and on the grid you'll see some resistance there or something. First of all, in your IF circuit, generally the grid voltages are established by the ABC voltage that comes from the detector and through the filtering circuit. There'll be some sort of load resistor that goes to ground on one side, and it'll develop a voltage across it, and that'll be a base negative voltage. Sometimes they're hooked in, such as this radio, they just, to guarantee at all times, maybe the ABC is not as strong, or maybe they want an absolute guaranteed baseline negative bias voltage, they'll do what you've seen a lot of radios coming off. They'll have a voltage divider set up to get some of those voltages. Now this one's actually for the B+, but there is a negative going up here. This radio actually is picking only up off the ABC as opposed to anything else. Some radios, they will establish some other means of getting the negative. Some will go with what is, a cathode biasing, where you put a resistor in the cathode before it goes ground. There's various different means of doing it. As far as the plate load, it's basically what they call reflected impedance. It comes back. All transformers do this. Whatever the load is on the output will be reflected back through the transformer in relative terms to the turns ratio. It'll be multiplied times at the square of the turns ratio and reflected back onto the plate. So that's how the plate gets its load, is through the transformer. Everyone knows, or should know by now, or anybody that's working with tubes or anything should know, that your grid, a grid of any tube, is fairly high impedance. That high impedance is going to reflect back through the transformer. Generally IFs are 1:1, so we don't have to worry about the turns ratio, so I'm getting a direct feedback of this impedance back onto the plate, which gives me my plate load impedance that I need for it to operate. Anyway, I think I pretty much covered most of the stuff I wanted to cover. They're not magical, really, and there's various different designs and different techniques that's used, but they're really basically a tuned transformer, and some of them will be either only tuned on once, either the primary or the secondary, where the other coil is not. Most you will run into are tuned on both. And their basic job is to pass only one frequency through, and that's your IF frequency. So there's not much else to talk about. I will delve a lot deeper into them in the transformer series I'm doing, and we'll get into a little deeper into some different losses and things of this nature, and the basic design considerations and everything of them. So anyway, until the next time, thanks for watching. This video got really long. It seems like when I start talking, I don't know when to shut up. I need to start scripting a lot of this, keeping a script so I know what I'm saying, what I want to say, and make sure I get everything in there I want to talk about. So anyway, I want to thank my new subscribers, and I want to thank you guys for your comments and stuff. I've been trying to reply to some of them, so keep watching, and more to come. Thanks for watching.